Textbook physics typically sorts matter into three neat boxes: solids, liquids, and gases. We watch ice melt into water and water boil into steam, and the transitions feel like clean, fixed events. But high-precision observation reveals that these boxes often break down. In the late 19th century, physicist T. O'Connor Sloan noted that a block of hard asphalt left on a street will slowly flow over months, and a stick of sealing wax supported only at its ends will gradually bend under its own weight. These materials demonstrate a core thermodynamic rule. Matter exists on a sliding scale. Its behavior depends entirely on the specific amount of heat applied and the resulting speed of its molecules. Labels like solid or liquid effectively describe temporary phases in a microscopic tug-of-war between atomic forces. You can see this tug-of-war playing out at the upper edge of any liquid resting inside a narrow glass tube. The shape of that edge is decided by two competing forces. First is cohesion, the internal attraction that liquid molecules have for each other, pulling them inward. In this animated cross-section, the second force is adhesion, the outward pull from the glass walls. When adhesion overpowers cohesion, the liquid climbs the glass, creating a bowl-shaped concave meniscus. Swap the fluid for mercury, and cohesion wins, warping the surface into a convex dome. Every visible surface of a liquid functions as a live geometric map, showing exactly which physical force is currently winning the battle. To see what happens when we push these boundaries to the extreme, we look back to the thermodynamics laboratories of the 19th century. Researchers of that era began to understand heat mathematically as kinetic motion. At absolute zero, -273 degrees Celsius, all molecular vibration stops. As heat increases, those resting molecules begin to vibrate, forming a solid. Add more heat and the molecular pathways lengthen. They begin to slide around each other as a liquid. Add enough heat and they break free entirely, bouncing around as a gas. To test the absolute limits of this kinetic progression, scientists used a device called Naderer's tube. It is a sealed glass tube half filled with a liquid, designed to be heated under intense pressure. As the tube approaches a specific thermal threshold, known as the critical temperature, the environment inside becomes turbulent. Flickering ripples and strange visual bands, called stria, rapidly form within the glass as the liquid nears its limit. Right at the exact critical point, the molecules no longer prefer being next to each other over being in the vapor. The cohesive force holding the liquid together drops to zero, and the meniscus abruptly snaps flat and vanishes. At this specific temperature and pressure, the physical boundary is completely erased. Liquid and gas have merged into the exact same phase of matter. While a sealed tube forces phases to merge, an open environment can force them to violently separate. If a surface is heated past roughly 200 degrees Celsius, it reaches the Leidenfrost point. When water meets a surface this hot, it enters what Victorian physicists called the radiant stage of boiling. The instant a water droplet approaches that glowing hot metal, its bottom skin flashes into a layer of vaporized gas. In profile, the trapped gas acts as a microscopic cushion. The droplet exhausts steam downward, creating a low-friction shield that levitates it. Because steam conducts heat poorly, this vapor blocks direct contact. The hovering droplet relies completely on thermal radiation leaping the gap. In the radiant stage, the liquid survives extreme heat by actively rejecting physical contact and weaponizing its own boundary against the metal. Whether it's a vanishing meniscus inside a high-pressure tube or a levitating droplet skittering across a hot pan, these phenomena point back to Sloan's core observation. Nature does not jump. Solid ice, liquid water, and gaseous steam are composed of the exact same molecules. The primary factor distinguishing them is the kinetic speed at which those molecules travel. These experiments show that the boundaries between states shift and blur as temperature changes. Ultimately, matter is defined less by fixed categories and more by a universe in continuous motion.